Hello, guys. Hello, everybody. Hello, Philippines. Hello, world. Welcome to my YT channel. This is again, I'm a singer, Eternal Voice. Welcome to my CHE Diary, Chemical Engineering Diary. So, our topic for this moment in time is still about Arhenius theory, which is one of the coverage topics of physical chemistry. Okay, so in this topic, actually, this is also discussed in chemical reaction engineering or chemical kinetics as separate subject. But the preparatory or the overview or the basic are being discussed in physical chemistry and also in general chemistry. You can still remember one, it's still there, it's discussed also. Okay, now before going further, I need to show to you our section to discuss. Okay, our learning outcomes for this live stream. Okay, so these are at least 5 learning outcomes. Okay, take a look, zoom in. Okay, like that. Okay, our first will be the principles and concepts. Second will be our formulas. Third, quantities, relationships. Four, graphs, solvings. Seven, others, or anything, or etc. like that. Okay, first let's discuss about the principles and concepts. What is really our Arrhenius theory? Okay, anybody? So the Arrhenius theory was discovered by Arrhenius, Mr. Arrhenius. His complete name is Mr. Svante, Svante, Arrhenius, in 1896. Okay, what this all about? Okay, he created and discovered that the rate of reaction constant, okay, is have a relationship with the temperature in many physical and chemical reactions. Again, this describes the relationship or the relation between the rate of reaction constant and the temperature in many physical and chemical reactions. So not limited only to chemical reactions, right? Okay, something like that. So these are all about Arrhenius principles and concepts. Okay, before going further, we need to know what are those quantities we need to learn. Okay, first, temperature, catalyst, something like that, and pressure, the division energy, like that. Okay, and the concentration. Okay, now we go to the formulas. Okay, actually there are wait, there are 5 formulas for this. Okay, the 4 formulas for this are derived from the base foundation formula created and postulated by Mr. Arrhenius in 1896. This talks about the rate of reaction constant. Some books refer as rate constant, non-rate constant. Okay, but it's still a more precise. That's why reaction rate constant. Okay, the first formula would be, wait, okay, it's gonna be like a rate reaction constant is equals to the pre-exponential factor times the exponential negative activation energy over the universal gas constant times the capital T. Okay, this is okay. I'll show to you and memorize this also. Okay, while you are still in your first year college, in your BS chemistry or BS chemical engineering courses. or any related sciences courses, because it could not be denied. This topic really is very important in dealing with chemical reactions. Okay, because in this topic we need to determine how fast or how slow the chemical reaction really is. Okay, that's why we have so many factors affecting the rate of chemical reaction. Okay, that's what I mentioned earlier: the temperature, the activation energy, the concentration, the adding of catalyst, speed of the chemical reaction, and so many things considered. Okay, now if the problems will have a unit of degrees Celsius, degrees Fahrenheit, degrees Rankine, then you have to convert that to Kelvin, because in here the capital T is Kelvin, standard temperature used. The same with the PV in RT, okay, in thermodynamics, something like that. Okay, or the same in Q is equals to, but somewhere along the derivation, it will be disappear, something like that. Guys, in here, we employ mathematical expression. Okay, we need to remember algebra in this particular topic of Arhenius theory, the application of basic mathematics, and also the integral calculus. Okay, for this. Okay, so that was 20 years ago. I forgot all those formulas and integral calculus, but I started to review basic some formulas of integral calculus. I learned only at least less than 10, the most common one. But then in algebra, so it could not be denied that you cannot forget the slope, right? Because it's also discussed in your high school, right? Integral calculus is not discussed in high school. Again, integral and differential calculus, it's not, it is not discussed in high school. It's only discussed in college. But algebra and trigonometry basics are discussed in high school or even grade school level or elementary level, grade 6. Okay, starting introducing some formulas for algebra already, right? And also in fourth year high school, third year high school, whatever, like that. Okay, something like so. Let's have first the formula of at least 5 basic integral calculus formulas that we'll be able to use here. Okay, the first is natural logarithm, okay, ln. If we have the logarithm log, the log, we have also the ln, natural logarithm. Okay, so first, and somewhere along our derivation of equation and formulas, we will be able to use this, okay? So that we can come up another equations to be used in this particular topic of chemical kinetics regarding Arrhenius theory. Okay. Arrhenius theory, guys, are really the basic foundation before going to the order of the reaction, method of initial rates, the half-life. For example, zero order reaction, first order reaction, second order reaction, third order of the reaction, something like that. You need to determine that one. So this Arrhenius is the starting point of all those order rate of reaction, and also for the rate law equation. Rate law means rate of chemical reaction. Okay, something like that. Or rate law. Something like that. Second formula, the LNA over P. Okay, number 3. 3, right? So ln 2 times ln Guys, in exponential, you have to carry the negative sign of the exponent. Okay, if it's negative, then negative 2 ln 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 exponential capital A is equal to the same as E raised to the power B equals to A. Okay, something like that. Okay, is equals to A. That's gonna be 4. 4 lang siya. Okay, because the others will be reversed. Okay, that's okay. So, ln E B times B. Okay, look at this. Number E exponential to the B is equal to the capital A. So this integral, okay? Now, this is the first formula, the original formula, right? This one. Okay? Now, how can we get the another formulas? So, we need to have a graphical representation. Usually in chemical kinetics, we need to have graph for example, the activation energy versus the reaction constant K, or it could be in here, right? NK versus one pressure, something like that. Okay, you need to graph. Okay, so before graph that one, we need to have the quantitative relationships. Okay, what are those? Okay, now we have our equation here. Okay, T is equals to A raised to the power E A R T. Now, if it is a zero order reaction, first order of reaction, second order reaction, it depends the unit of K. Okay, and then the unit of our EA activation energy specific kilojoules per mole. You don't have to convert this because it is specific. Okay, meaning say, for example, if the problem will say what is the activation energy, something like that, so your answer will be kilojoules supposedly, but then if it will, the choices will be joules, then you have to convert. What I mean is, somewhere along the way, you need to consider that this is a kilojoules. Okay, you get the point? Then if the choices be, it is really the standard kilojoules per mole. Okay, and our R is like this R, right? But we memorize two values, right? So the first value will be the 0.08205 liter atmosphere over mole Kelvin, and the other one also is 8.3145 joules per mole Kelvin. Then, since our activation energy is joules, then you have to use the 8.3145 because it is closer to that. Okay, yes, the problem will give other units, and you have to force to convert the quantities, and then cancels out common units somewhere along the way of your computation. Then bingo, you can solve for what is being required. But in here, we're talking about is 3145 joules per Kelvin, and our T is Kelvin. Okay, something like that. So I have to put this in a square. This is our parent formula. Okay, like this. Okay, now it is relationships. Okay, and the rate constant. Okay, in your chemistry, you remember that one? Okay, RT, something like that. Stoichiometric relations of a solute and solvent. Then because solute doesn't mean what? Ethanol, there is with gas mixture, with solid mixture, mixture, gas mixture, something like that. Okay, that's why we have physical and chemical separation point. Now, guys, what will happen to the activation energy? If you try to put this in the emphasis of energy, this amount of energy, which activation energy, is equal to the kinetic or to start the chemical reaction. Okay? Or else, If it is not that definition, then of course your activation energy will increase also if you increase the temperature, right? Somewhere along the way. Okay, but here the activation energy will decrease. Okay, get the point? Okay, our activation energy will decrease because we are referring to the lowest activation energy, mga siya. Okay, constant. This is increasing the temperature. Okay, number two. Okay, then, okay, in this situation, if you increase the temperature, what? Okay, K, rate constant. What will happen to your rate constant if you increase the temperature? Okay, we're talking about quantitative relationships so that your answer will become wrong because it's expected to be lower instead of high. Even though you're using difference of equations, somewhere along the way, your final answer will be wrong because it is not meeting the quantities relationship constant man siya. Okay, so this is the rule. Just like in the fluid flow. For example, if the liquid will pass through the, for example, venturimeter, answer, solving like that. If your answer is very high or it's very low, sorry, even though you're using the correct equation, because somewhere along the way you are so fast in solving like that, okay? Because the diameter, the area is inversely proportional in bracket capital A inside, something like this. This is concentration. If you increase the concentration, guys, there's no effect in the rate constant. There will be no, but your rate is high. Of course, you increase your concentration. Normally, it will become fast because concentration is referring to the strength. Okay, the strength of your concentration. It will increase, as I told you. We increase the surface tension. What will happen? Acceleration